Hello and welcome back. We are writing an operating system from scratch. Actually, it's been quite a few weeks since I've done anything on this project. So today we're going to work on something very light, as in simple, but still very important for the rest of the project. Actually, primordial. And we'll get to what that is in a moment. Before that, I guess I should do a bit of a recap of a few things that I did off camera, a few bugs that I caught, and a few config changes that I made to move from assembly to C. We're going to start writing C code, boys. Let's go. Okay, let's take a look at the changes. So let's see here. I guess the main change is that I caught a bug here in the video mode change code that we did. Instead of copying the frame buffer height into the FB height field of our boot info, we've copied to basically overridden the FB width, which is bad. And also I've removed this infinite loop that we had here. And I replaced it with a jump to a label called cmain. And here at the end, I added so an alignment tag to 32 bits, some padding, and then this tag here, cmain, at the very end of that file, assembly file, so that basically when we combine the assembly file and the combined C file, or I should say the obj file that results from the C source, we can basically jump into the entry point of the C code without having to specify an address, an absolute address. Let's see what other changes there were. So I've made a few, I guess, style changes to some make files to uppercase the output there. And I added a make file to basically be able to compile the C code. So basically what we have here is just a make file that will take all the C files, run them through Clang to basically generate obj files, take all the assembly files, run them through Phasm, and then combine all of those with a linker script to get an elf file, and then take the elf file from the C code and then combine it with the start .asm code that we already have into the stage 2 bin. We are basically just doing a cat to combine those two files. And that's about it, I guess. So yeah, I also added the linker script for this. So basically, here we have our entry point will be underscore cmain. Here I've hard-coded the address at which I expect the cmain to be, which is 0xBA0. Yeah, just some, I guess, syntax changes. And I've also created a main.c file with the entry point, which is underscore cmain. All right, so all in all, I guess we should update this. Here we have switched to project mode. Yeah, so all this is done. Now, let's talk about what we're doing today. So today we are working on printing stuff to the screen. Last time we've changed the video mode setup so that now we have a graphics frame buffer, linear frame buffer, except that when we did that, we lost the ability to print to screen using the byte services. So now we will actually need to do some work to be able to write pixels to the screen and write characters from those pixels. So the first thing we're gonna need to write characters to the screen is, now actually let's first start by just drawing some pixels on the screen. All right, let's do that. So okay, let's get started. So here we have our CMake file. What I will do is I will create, I guess, a new file. Let's call it console.h. Yeah, and I guess we'll need to do so if not defined, console bound define console. There we go, and if right. So here, I guess we are going to define just one function for now, just void function, and let's call it fill. So what we're gonna try to do is we are going to try to just fill the whole screen with a single color. Right. Let's go ahead and create a C file for that. And here, of course, we're gonna have to basically include the console.h, and we define fill to be. All right, so here we need to think about a few things. Let me just go back to my linker script. So here in my linker script, I added this boot info with the address where we've put the boot info struct we've created on in our start ASM. So basically, it's this thing that we put here. So now I guess we are going to need to reference this from C. So we will have to create the struct in C. Let's do that. So let's go here, create. Let's just go with info.h, and of course, again, if not defined, and this should be just call it boot info for now. It's fine. Right, and we define it also. There we go, that's good. All right, so here what we are going to have is a, so let's type def struct. Oh yeah, and we also definitely want it to be backed, since we didn't do any job on making sure that it's backed. I think we have a single byte in the middle of the struct that will basically move all the other fields below it if we don't back it. So attribute, I think that's how it is, and then of course, oh yeah, I'll probably need to give it a name, boot info, and I guess here we need to have a few fields, but I forget which fields we need. So let's open up this struct and have this be our reference. So here we have magic bytes. We have 4 of them. So we'll create, actually, let's do something else. Let's do something else. I'm gonna create a new files and I'll call it types.h. And I'll just open it up here. And here we'll do if not define. Just give me the snippet, please. And this would be types, I guess. There we go. And define types. That's good. Okay. Never mind. What was that? Okay. Right. And what I'm going to do here is I'm going to do a bunch of type defs, because I find that C types are very tedious to write, very long to write. So I'm gonna do a bunch of type defs for them. So unsigned char b u8. Oh, and basically I'll just type def them to I guess Zig/Rust nomenclature, so that we can work with those. So type def unsigned short to be u16, and type def signed just short, I guess, short to be i16. Right, so that's it for the shorter ones. Here we do the u32 and the int as i32. And here for the longer types, for the wide pointers, I guess 64-bit types, unsigned long, if I'm not mistaken. We'll do a quick check in just 1 second to check that those are correct. Right, so let's do a quick check. Let's do define 64, let's call it size 64 to be size of u64, right? So is there any way we can actually get the information from the LSP here? All right, never mind. We'll check it afterwards. But I'm pretty sure that's how it is. Long should be the longer types. All right. Okay. Let's get rid of that. And now let's go back to this. So what was my file? It was struct. That one. Cool. So let's do that. Here we have u8 magic, and we have 4 of those. u8, we have 4 of those. Then we have a u32 size. Then we have just one byte, which is the bootloader type. And okay, so we have u64, which is the frame buffer pointer, another u32, which is the frame buffer width, u32, which is the FB height. Am I missing something? No, that's fine. Then a u32, which is the FB scan line. I guess I should call this scan line bytes, just so that it's clear what it is, what it means. Here we have just 1 byte, which is the frame buffer pixel format. Right, and here we have some unused fields. So what do we have? We have 4 quads. So that's 4 times 8, that's 32. Then 2 more, that's 34. So unused 0, which is 34 u8s. Right, then we have the ACPI, which is just a u64 again, ACPI pointer, and we have so 3 quads. So that's 3 times 8. So let's do unused. Let's go unused 1, and that's 24. That's 24, I guess. Oh yeah, of course. And here I am going to need to so include types. Types.h. That's correct. All right. We are going to need to create basically the definition for the boot info. So let's do that, because we have defined it as in our linker script. So now we are going to define it inside our code. So extern, I guess it's not volatile because it's not really written to, it's just read-only memory. So I guess extern boot info. So now let's go back to so console C, and now let's try to write this. So here u64 fb will be our boot info.fb pointer. Okay, and I guess we are also going to need to actually not here. Let's go here and include. So we're gonna include types, and we're gonna also include boot info. Okay, that's good. So let's go. There we go. Let's do this. Let's write a for loop that will basically go from so u32 j, which is the outer loop, will go into loop over the I guess the rows, and then start to go from 0 to so boot info.fb height, right, and plus j, right, and here we're gonna do another for loop. Yeah, actually, don't do that, please. Right. So for loop with a u32i from 0 to so boot info.fb width, and what we're going to do here is we are going to so let's first do this. And here what we are going to do is we are going to compute, we don't need to compute it. We know what we're doing, right? So we know that our pixels are 32 bits because that's what we asked for when we queried for the video mode. So we know that every pixel is equivalent to a 32 to an int or to 4 bytes. We'll just point to them as ints for now. And here we'll have fb plus I plus j times so j times boot info dot fb scanline bytes, right. And here we might need to, because I is the pixel and we are referring to the bytes inside that pixel. So I will have a stride of 4 because 4 pixels per 4 bytes per pixel, and J would have a stride of FB scanlines bytes because that's the number of bytes in one row. Okay, so that would basically need to be So, okay, so we'll write that to there. And of course we need to do something like this. Yeah, so if this works, we should have a screen that's full, that's fully white, because this is what we are doing here. Notice that we are still not using the information that we got from the setup, which is the pixel format. And I guess we don't really need it because all the pixels have the same, all the components of the pixels have the same color here, so it doesn't really matter for us. So let's go back to main, and call, or should we probably do something like include console.h, that's good. And here we can just go ahead and do fill. Oops. Fill. There we go. What the hell? All right. Right. There we go. So fill. All right, that's cool. Let's try to build this and see what we get. All right, it's built in, so let's run it. Let's put this here and FQ64. Yep, that's good. Okay, so we are expecting to see a screen that's fully white. So let's continue here, and we have a screen that's fully white. Great. So now we have a way to write to the frame buffer. Or at least we know how to do that. So now what we're going to do is go back here and try a few things. So instead of doing this, we are going to try to do something like, yeah. Okay, and now let's go back here, rebuild that, and rerun that. Great, so we have a, I guess, a light shade of gray that we can work with. Cool. So now we can print stuff to the frame buffer, I guess. But what we want to do for now is we want to print characters. So for that, we need a font, except that modern fonts store their glyphs in a bit of a tricky way to basically allow you to rescale the size of the glyph however you want, basically, except that we don't really want to deal with that for now. So the solution to that is to use the most basic font format that I could find, and that is the PSF format. So let's take a look. Right, so yeah, it's a bit bright, but so the PSF font format is basically just a header followed by the data for every glyph. The glyphs are fixed in size. So basically you have pixels that map pretty much directly to bits that are set on the glyph. And we have, I guess, the ASCII code of the glyph, or Unicode if you have a PSF font that supports Unicode, but we're not going to use that, is basically how you're going to index the font in the file. Yeah, I guess that's everything that there is to know about that. So let's just yank all of this and go back to here, do something like this, create a new file called psf.h, and then I'm just gonna put everything in there. I'm probably gonna change these here. yeah, so let me just do that real quick. So this is a U8, and then we can just do something like this. So unsigned signed int goes to user2. There we go. And of course, we are going to need a so if not defined, PSF, not PDF, PSF, right? Oh yeah, actually we need to define it. So define the PSF, and if we go down here to, there we go. And I guess now we are going to need to basically include the types.h, and that should be fine. Yeah, I'll do something else actually to make life easier. I'll type def a struct, and this struct here will have, I'll call it PSF, right? PSF2, I guess I'll call it. Yeah, and this one here would have a struct PSF PSF2 header, field called header, and then it'll have I guess a U8. So it should be a U8 pointer, which would be glyphs. Right, yeah. Because just at the end of the header, we have the glyphs that are laid out. And that's what this will basically point to. Should probably also make it so that, let's go, attribute packed, just to make it so that it's packed. It should be packed without us having to do this, because every single field here is aligned to a 32-bit boundary. So yeah, it's fine. We don't really need the attribute packed, but it's not hurting us, so let's keep it there. Right, and I also want to take a look at a font that I found. Oops. Right, so here I have this PSF font. So let's take a look at it really quick. So let's go this way, and I guess the first thing I want to do is just do xd font PSF. Yeah, probably do that, but with a more. And let's take a look here. We have actually, let's also do something like this, and do so what we want is bootloader stage 2 set and psf.h. Right, so let's look at these two. So first here we have 72, B5, 4A, and 86, which are our magic bytes. So we have 4 of them. And then we should have 4 bytes, which are the version. And the version is always 0, I guess, for PSF2, from what we have in the... yeah, this will get bright. Yeah, so in the documentation, they basically say that the version is always 0 for PSF2. But we don't really care about that. So let's go back here. Here we have the header size, which is basically 0x20, 32 bytes. Oh yeah, keep in mind that these are in Little Indian. So this is the least significant byte. Right, so then we have the flags, and then we have the length, which is 0x100. Yeah. And then we have char size. Char size is the number of bytes for every glyph, every character. And that is this 0x10, which is 16 bytes per glyph, which is pretty small, but yeah, it's usable. And then we have height and width. These are in pixels. So we have height is 16, 0x10, and width is 0x8, which is 8. And here, starting from 0x20, which is basically the offset of the end of the header, we have our first characters here. And we should have one character every 16 bytes. So every line here is a character. Right, so let's take a look at just one of the characters, right? Let's take a look at a character that we know. For example, capital A. So capital A is 0x41. So if I do 0x41 times the length of one character, which is 16, I get 1040. And then to that, I add the 32 bytes, which are the, I guess, the size of the header. And I get 1072. So let's try to do that then. Right. So XSD, except that this time we're going to take bits and we're going to have it seek 1072. And we're going to want a length of 16. And I guess we should have columns of 8. And of course, font PSF. Yeah, that's actually pretty bad. We actually, yeah, okay, so the columns are in bytes, not in bits. There we go, that's much better. And you actually can see, actually I don't know if you'll be able to see this on stream, but if you look just at the arrangement of the ones, you can see that we clearly have an A shape here. And if we, for example, take a look at, let's increment this by 16. So let's have this at 8, 8, right? So here we have B. So basically we have our characters, and every bit, so these are not bytes, these are bits. One whole row here is 1 byte, okay? So every bit basically maps to 1 pixel on screen. So this is what we are going to have to do. We are going to have to translate every one of the bits that we have in this file to its corresponding pixel on the frame buffer that we have. Okay, so let's do that. Actually, before we start doing that, there's a neat little trick that we are going to have to do. Oops, get out. We still cannot read files from disk. So what we are going to need to do is we're going to need to embed the font file inside our object file that is produced by our linker. So to do that, we are going to coerce, or we are going to make the linker think that our font file is actually an object file. And to do that, we are just going to use some obfcopy magic. So let's do that. So here I will do something like font.o, I guess I should call it. And here we're going to have obfcopy -o, and here we are going to tell it that it's an L32 I36 386, sorry, and we're just going to have to tell it that it's, don't worry about it, it's a flat binary file. And so where is it? It's there. there. All right, cool. Font and font.psf. That's cool. And we are going to just have it in the current directory, I guess. Yeah, that should be fine. Right, and now we are just going to go here and delete that font.o is actually an object file that should be linked with our other object files to get the main.elf. And then when we will copy the main.elf to make our final stage 2 file, it will be in there. So let's first run this and see what we get. Okay, so here we go. Okay, it looks like it builds correctly. So let's do objdump -d and go to what was it? Bootloader stage 2 and font. Okay, maybe with this would be helpful. Right, so here we can see that we have our, so this is a section, right? Section name. And we have this name that was auto-generated by the objcopy stuff, which is basically our, the folder hierarchy to get to that file, which is font.psf. And here you can see that we have our magic bytes, which are 72, B5 for A and 86. So basically, ignore the instructions. These are bogus instructions. But you can see that we actually have the data we had in the PSF file now inside our object file. And if we do the same thing for, so let's do the same thing, but for main build main .elf, and here I'll just do grep PSF. Yeah, there we go. All right, so now that we know that our file is there, yeah, actually, let's go back just one more time. There we go. So let me just copy this, and then we can go back here. So what we are going to need to do now is go back to the PSF. Yeah, probably not this. PSF.h, yep, that one. And here we're gonna do the same thing that we did for our boot info. So we'll declare an extern. And here we don't really have much choice. We're just gonna have to declare it as a U32, I guess. Yeah, let's just declare it as a U32. And let's just paste that in. Yeah, that should be good. All right, so now that we have that, let's go to console.h first and do void print char. And this would take a U32x position, a U32y position, and a U8, which is the character to print. And we're gonna go to console.c, and here we're gonna do print char. That's great. Yep. Right. So here we are just gonna do something very stupid, but we're gonna make it easier for ourselves. Let's just do this, and now let's get working. Okay. So first of all, let's declare a PSF. All right, we gonna get there PSF2 pointer, which would be the font, which would be which would be a PSF2 pointer cast of the address actually. Right. So now we have this font that we have declared from the address that's pointed to by this variable here. And we have also our frame buffer. So now we can start working on these things. So first of all, we want our glyph, right? So U8 pointer glyph would be equal to font. So I guess glyphs we've called it. Plus. So what we said is C times font header. Right, so let's do PSF. There we go. So we call it header. Yep, that's correct. Right. So header, and we want char size. Yep, char size. There we go. There we go. So here we have the glyphs, which is a U8, and then we offset that by the character size times the ID of the character that we are writing. And now we just have to basically write that glyph. So here we're going to change a few things. Here we are going to, instead of looping through the whole height of the frame buffer, we're just going to have to do font, header, and what? And height. Yep. And this, so here would be font, header, width, and what are we missing? Oh yeah, and this one here would be actually something else. Right, so this here would need to be different, because instead of writing to every pixel that we encounter, we are just going to write to specific pixels if they are set in our character. So let's see here. We're gonna need to see if. All right. So here's how we're gonna do that. We're gonna create a mask. Should be somewhere here. Right, so U32 mask, and this would be one. So basically, we're gonna select bit by bit, starting from the most significant bit, which is the basically the leftmost pixel in our glyph, and ending with the least significant bit. So we're gonna shift that by font width. Maybe it should be header width, and of course -1, because we want to basically the least significant bit should be at 0, at a shift of 0. So it's just 1, and to have that we need to subtract 1. Right, and here we need to check if our mask is actually doing anything. So if, no, actually we're not going to do it that way. Here's how we're going to do it. Oops. Here's how we're going to do it. We're going to go all the way over here. And then we're going to say, so current, So we are going to end the current line. So that and mask, and if that is true, we are gonna print basically white. Otherwise, we're going to print black. Okay, that looks pretty okay. Right, so now we need to figure out what our current line is. And our current line would actually just be, oh, and something else, we actually also need, so U32, yeah, let's do a U32, call it current FB, let's say pixel, and that would be equal to FB plus basically the X times 4 plus the Y position times so the FB boot info FB is Kernel bytes. Yeah, I guess that's it. Right, so this is the current pixel at which we are printing. So here we can get rid of all of this and just replace it with current FB pixel. There we go. And actually this needs to be a U64, otherwise we can have some weird issues. Right. So now we just need to basically point into the glyph line by line. So let's do that. So here we create U32 current line. Current line, and this would be something like that. So what do we put here? We should put glyph plus what's our glyph? Our glyph is a pointer to a U8. Okay, so maybe here we should also keep that pointer to U8, and we displace our glyph with J times. So we need something that's glyph with in bytes. Right. So let's compute that here. And that would be U32. It should be less than that, but it's fine. So glyph with in bytes, and this would be. So let's think about this. This would be glyph, or should be font header width, which is the width in pixels. And this should be multiplied by 8, because every no, actually, it's not multiplied by 8. It's divided by 8 because we have 8 bits in every pixel that we have here. So if we want to know which byte to be at for a given pixel, we are going to have to divide it by 8. So this would be divided by 8, right? And just to round it up, because we want this to be rounded up, we are going to do, so let's just add 7 to it. That should be fine. Yeah, that should be fine. So here we have the glyph width in bytes. So basically how many bytes we get for one glyph. In ours, we know that it's 1, but we might get some other PSF fonts that are more than 1. That's why we are doing this computation here. And then we have our current frame buffer pixel. And then we are going from, so for every row of the glyph, and for every I guess column of the glyph, every pixel, we are writing it. And I guess we just need to do something like mask. We shift it back by 1 to basically get to the next pixel over on the same byte. And at the very end of that, we should also do we should also move the actually we've never moved the current frame buffer pixel, and that should be moved by 4 because we're pointing to a byte, and a single pixel is 4 bytes. And here we are going to need to move current line. Actually, we don't really need to move current line because it's recomputed every time. But we might actually want to just take this out here, hoist it out of the loop. Right. Yeah, we're gonna hoist that out of the loop and just go over here and do so current line plus equal glyph with bytes. There we go. That should be fine. And I think with that, we should be able to print a single character to screen. Actually, I just noticed something here. This, we should have it as a U8. Otherwise, we're going to have some weird stuff going on. And otherwise, I think we're doing pretty nice. All right. So now we are going to test our print char. So let's take a look at what that gives us. Right. So let's just make all and run QEMU and see what we get. And we don't really get anything for some reason. Okay. So let's take a look at what we did wrong here. What went wrong here? Frame buffer. Okay. Not really seeing anything weird here. Except if this doesn't give us the correct address, I guess, to our glyph. Right, so maybe if I try something like U32, and then we go ahead and do something like this, and then we course it back to be a U8 pointer, maybe. Yeah, that should be fine. That should be fine, I think. Right. So what else did we do weird here? We have our frame buffer here. I think that's fine. Okay, so let's retry this, and if it still doesn't want to work, we're just gonna have to debug it. Okay, so let's bring out the debugger, I guess. Right. Okay, so that's good. Here we're just gonna do something like this. And gdb target remote localhost 34. Yeah, I think we're gonna have to do something before that. Let's see. We are going to have to change this from being run on a 64 machine to a 33 to a 86 machine, just so that GDB doesn't get confused with the instructions. Right. So let's go back up here, 1, 2, 3, 4, and right, and let's put a breakpoint at 0xBA0 where we have our main, and continue. Right, so here we have BA0. So let's just let's just put a breakpoint directly on 0xC50, which is, I guess, the call that we're doing to the print function. And here we have our print function. So let's take a look at what it's doing. Right. So it's taken E1C. I wonder what's in E1C. But that looks like our font might be in there, just judging from what it's doing. Right, so here we're moving something to EAX. Right. So let me just do something here real quick. I'll just quit this one here. There we go. So now we can see what we have in our registers. So what we have here is that we are moving something from the stack to, sorry, not from the stack, from the variables we got called with to EAX, which is the Y argument. And then we are going to, so X goes to EDI, and then in ESI we've put basically, so here we're doing the round in the bytes. The glyph with bytes is what we're doing here. It's what we have in ESI, so we can see that it's 1 byte. It's good. So here A00D should be, yeah, so A000 is where we put our boot info struct. So 00D is probably the frame buffer address, I guess. So we've put that into ESI. Okay, so it's not the frame buffer address, I guess. Okay. Okay, so in EDI we have so FD 000000 is the start of our frame buffer. Here we have offset into it by 12 bytes. So let's see. Okay. We're not doing the write into our frame buffer ever. So let's probably let's go back and take a look at what we have in the code. Okay, so let's see here. I guess the first thing I want to do is actually go over here and just get rid of that, because we don't really care about the absolute address of this pointer. We just care about its position in this struct. So we don't really need that as a pointer. And then we go back here. So that basically means that we can just get rid of this. And it just works. Oh yeah, now I guess we should take the address of that. And that should be fine. So what are we doing here? Oh, okay, I see. We are actually just printing the same pixel over and over again. Right. So let's do something like this. Let's call this current frame buffer line, and then create a U64, which would be current frame buffer. Yeah, let's call it pixel, and then this would start as current frame buffer line. And here we should always do current FB pixel equals current FB line, just to reset it. And at the end of this, we should do current F buffer line, and this we need to move it with FB's count line bytes. So basically, we need to go to the next line on the same on the same X offset, but on Y plus 1, basically, is what we're doing here. Okay. And so here we are taking that. Here, let's just do something here, just so that the compiler doesn't mess with us. Okay. And actually, there's something else I want to do, and that's let's just write something like this here, so that we can see what we're doing instead of just writing all black pixels. And I guess this should be fine for now. So let's build and run. Let's see what we have. Okay, so we have something. Oh, okay. I think I see what this is. Right. Yeah. Okay. So this would need to actually be multiplied by font header and width, basically, because now we are not we are writing a character inside the next one, because we offset them by just one pixel, but we want to offset them by a whole character width, actually. And I guess the same thing needs to be done with the height. So this would need to be font header height. Yeah, something like that. And I actually went ahead and changed the main to add a loop here to print the characters. So printing 100 of them. So let's compile this and see what we get. Okay. All right. Okay. We are actually getting something usable here. I just zoom in this. Yeah, I don't know if you can see it on the video, but basically we have, we have A's, which is great. Great. Right, let's do something fun, I guess. So let's replace. Okay, let's do something like this, and do 256. And what we'll try to do is we will try to print. We will try to print the whole character table just to see what we have. And here we'll do u32 x equals, let's start off at, let's say something like 2, and u32 y equals 2 also. And here we'll do this from there to there, and we will print it at x and y here, and we will print I, and of course I here needs to be you wait. Yep. Oh yeah, and also if let's see, if x is larger than, let's say, 50, we do y plus equal 1, and x is reset to 2. Yep, that looks good. And also, I guess what we need to do is x plus plus. Or actually, never mind. We can do something even better than that. We can just do this, like so. Right. Okay. So let's save that. Let's rebuild. Let's see what we get. Okay. Okay, so I think the compiler is actually trolling us because it's considering that this is an infinite loop since we are doing this comparison. So let's just change this to this and we'll have something that works. Okay, let's go. There we go. So now if I try to zoom in a bit, you can see that, I might get rid of that red color because, it's too much. But at least we have discernible characters. So now we can actually get to writing interesting stuff. Like, for example, we can write a printf function that we can use for our debugging. All right, so that's it. We have support for printing characters at locations in memory. So next time we will work on implementing printf, or actually a subset of printf, because at this stage we don't really need the whole thing. As always, if you have any questions or comments, leave them down below. If you like this series, do the thing, you know what to do. I noticed I didn't put the Git link for the repo in the description, so now it's there. All right, see ya, bye.